So here is the compact representation of the neural network that we've been interested in. On the left hand side, what we have done is encoded this temporal dependence or dependence with respect to the structure as a self loop on the perceptron. So the self loop says that the state at the next iteration depends on the state at the previous iteration, and the influence is through this weight W. Of course, the state at the next iteration would also depend on the new input. So this x could have been xt, and it could have been xt plus 1 at time t plus 1. So the state s at time t plus 1 will basically be a function of the state at time t and the input at time xt plus 1. So if you unroll this network, this is how it would look like. Xt minus 1, xt and xt plus 1 are the inputs at different time instances. The dependence of the states on each other is based on limited memory. So st only depends on st minus 1, st plus 1 only depends on st. St plus 1 does directly depend on the input at time t plus 1, that is xt plus 1. Its dependence on xt is only indirectly through st. So what you see on the right is what we've been talking about as the functional property or the functional characterization. And what helps you achieve this functional characterization is the structural property. Now, how does this actually happen for the language model demo that we just showed? Let's start with a simple setting, and let's say we have 3 characters, A or B or C. Now the input at any point of time is either an A or a B or a C. A very often used encoding for this vocabulary and the way you let the network know that a particular input was seen is through this so-called one-hot encoding. So we're going to have 3 bits, a vector with 3 positions. Each position is binary, so 0 or 1. The value at position 1, if it turns out to be a 1, it indicates that we have seen an A, and we would therefore require that there are zeros at the other 2 positions. Likewise, position 2, if filled with a 1 and zeros at other places, would mean a B, and a position 1 at the 3rd position with zeros in the other 2 is a C. So this is what is referred to as the one-hot encoding. Give a unique k to each character in alphanumeric order and encode each character with a vector of vocabulary size with a 1 for the kth element and 0 for all other elements. Now with this kind of language model, how do you predict the next character? Well, what you would like to do is pass on the input to some hidden layer, and this hidden layer of course will in turn affect the output, which could again be one-hot encoded. Let's say there are 3 positions here again, we're just trying to predict what are the next characters. So A would typically be followed by a C, and let's say this is what is desirable. How do you make the possible prediction at the current state influence the prediction at the next state? It's through the hidden layer. So hidden layer will have a self loop. This is the structural aspect. Functionally, this would mean that I look at its state at the next instance based on its state at the current instance, and kind of repeat this structure or unfold the structure to get the desired functionality. So here's ABC, and we're going to basically connect the input layer, which is going to be an abstraction of ABC to some vector with binary values, vector of size 3. We're going to connect this to hidden layer, which will in turn go to some output layer, but the hidden layer will have this self loop. So let's look at the unfolded network for a slightly more complex setting where you have many more characters, and let's say we are interested in auto completing the prefix MACH. Let's say we believe that this should actually be completed to INE, LEAR, NING, and so on. How does this happen? Well, we look at what character was typed in initially M, and there's some configuration of hidden layer. What we see here is 3 neurons in hidden layer corresponding to 8 input nodes. So this WHX we'll assume is a fully connected network, which means there are 8 into 3, which is 24 weights. So what you see here is one instance of time, but the same network was repeated at other instances of time. The output layer for us is again of size 8, and correspondingly there would again be 8 into 3, which is 24 weights. So as far as the initial state of the network is concerned, it doesn't seem to be doing what is desired. So this first cell, which has 0.3, should have ideally been 1 and the rest 0, but unfortunately what is being predicted at the second position is the character corresponding to this 0.5. We would of course like this to be corrected. Likewise, what is presented in green in these subsequent output nodes is the desired configuration, the one that should actually have been a 1 and the rest 0. Now how do you do this correction? Well, first of all, the WHH is going to connect each hidden node to itself in order to be able to more reliably predict the next character, and these WHHs are going to be trained to be able to get this right prediction. So what is the right prediction? Well, this is what we want. This is a desired state of the network after training, where corresponding to M you see an A, the one here with value 0.8, corresponding to an A you expect to see a C and an H and an I, and so on. So how do you make this happen? So how do you make sure that the configuration of the hidden nodes in that desired state, which leads to the desired output layer, is attained? Well, we have to train the WHX and the